In this lecture segment, we'll talk a little bit about the structure of computer memory, or RAM. RAM, as you may know, is an acronym for Random Access Memory. That describes lots of different types of memory, but the term has become a near synonym for the large working memory in which a computer stores currently executing programs and their data. Main memory is another common term. Any program reads and writes information to and from RAM. In a higher level language like C, this takes the form of reading and writing variables, which are named locations in memory. In assembly, it's a little more detailed, dealing more directly with memory as a raw series of bytes, though you still organize these bytes into variables. From an assembly viewpoint, the RAM is a large series of bytes, large meaning billions of bytes, although I've shown only 12 of them here, and each byte is individually addressed, also shown, with addresses starting from 0 and going up to whatever number of bytes there are in the RAM. You can think of RAM as a big array of bytes, if you like, with addresses as array indexes. But there is more structure than that. While each byte can be individually addressed and read and written by assembly instructions, the underlying hardware requires that bytes be fetched to and from memory in words of 8 bytes each, or in simpler CPUs, 4 bytes each. So let's break the RAM picture in the diagram here into words. Our examples will use 4-byte words because they're easier to draw and to talk about, and because most embedded programming does use 4-byte words to this date. Now, bytes are grouped into words because memory data comes into the CPU via a group of 32 or 64 wires termed a bus, each wire carrying 1 bit. So with a 32-bit memory bus, even if the CPU reads a single byte from memory, it gets 3 other bytes for free. A 32-bit bus is designed so that it fetches words beginning at addresses that are divisible by 4. So as the diagram shows, the addresses at 0 to 3 form a word and could be loaded. The addresses at 4 to 7 and the addresses at 8 to 11. So for that matter, do the bytes at addresses say 120,040 to 120,043. But say the bytes from 5 to 8, or maybe 21 to 24 further down in memory, those don't form words, and they could not be read and written as a unit by the RAM hardware, by the CPU and its bus. And similarly, a 64-bit bus would require addresses divisible by 8. As we saw in an earlier segment, large integers occupy 4 or more bytes. When the CPU reads and writes such integers, it must do so in words. And that means that multi-byte values in RAM must start at divisible by 4 addresses. We could, for instance, put an integer starting at address 4, but not one starting at address 5. And we'll see later that failure to follow this rule can cause program errors. Another historical note, by the way, the size of words has increased across the decades. Older machines had 2-byte words and 16-bit memory buses. Very old machines had 8-bit buses and read and wrote memory 1 byte at a time. First in-lecture question here. If a machine has 1 billion bytes of RAM, how many words is that? This is a slightly trick question, so answer carefully. So if you thought about it, the answer is that this would depend on the word size of the machine. Assuming exactly 1 billion bytes, a gigabyte is actually a little more than 1 billion. If we do make the assumption of precisely 1 billion bytes, and if the word size is 4 bytes, then the memory has 250 million words. But if the word size is 8 bytes, well, then there are only 125 million words. And an antique machine with 2-byte words would have 500 million words, although it probably wouldn't be able to handle that large a RAM memory. And while we're talking about memory concept, another important idea is the registers that reside in the CPU. In some CPUs, assembly instructions can work directly from memory. For instance, adding 2 memory words together and then putting the result into a 3rd word in memory. But this is quite slow from a CPU standpoint. The 100 nanoseconds or so it takes to read and write a word to or from RAM seem pretty fast to us, but a modern CPU can do 100 or more computations in that time. That's quite a mismatch, and it makes memory access a speed bottleneck. In a later module, we'll look at caching, which is a clever way to get around this problem. But for now, the simplest way to deal with the slowness of memory is for the CPU to have its own internal memory that runs fast enough not to slow the CPU down. Then the CPU can copy, slowly, from its perspective, information such as a variable from RAM into this internal memory, work quickly with the variable there across many instructions, and then write any changes to the variable back into RAM when it's done. This internal memory in almost every CPU takes the form of what are termed registers. I'll draw a little diagram of it here. These are typically one-word memory areas that can be directly worked on by assembly instructions. Recall from an earlier segment that our example add instruction added 2 registers and put the result into a third. Those registers would first have been loaded from RAM via other instructions, and then the sum might later have been written back into RAM, or perhaps just used without being saved. An ARM CPU has 16 registers labeled R0 through R15. Each can contain a 32-bit integer. An ARM processor also has some other registers we'll encounter later, but these 16 are the main working set for most ARM programs. Other assembly languages and processors, for instance Intel processors and the MASM language, have more registers, but the principle is always the same. Registers are the CPU's working space for fast computation, and the most important data the CPU is working with at any time is generally held in registers. Let's end with a thought question that sets up a time model we'll refer back to in later lectures. It's helpful to imagine time slowed down to what we might call CPU perspective, so that the relative speed of different operations that are to us instantaneous is more readily seen. So here's the question. If we slow time down by a factor of 1 billion, so that a CPU takes perhaps 1 second per instruction, that's 1 nanosecond per second, then how many seconds would a RAM fetch take? That's the figure we had earlier if you look back up in the lecture notes. And then what about a disk access? And that in normal time takes around 10 milliseconds. And notice that is milliseconds, not microseconds. So we're in a world where we have time going by at 1 nanosecond per second. A beam of light is traveling at just 30 centimeters per second going by. That's the CPU's world. How long does it take to get something from memory, RAM, and how long does it take to get something from disk? Well, if you've done the math, what you'll find is that the RAM access, since I did say it was 100 nanoseconds earlier, takes 100 seconds, or a minute and a half. And disk access is much slower. It takes 10 million seconds. Remember that a millisecond is a million nanoseconds, not 1,000 nanoseconds. So 10 million seconds is almost 4 months from the CPU's perspective. So by now you've probably had enough of preliminaries. In the next segment, we'll look at some actual ARM assembly code.